Okay, as you're handing that in, so we're going to it's going to change gears in terms of homework. A lot of the homework for the rest of the semester is going to be through an online system, okay, called web work. All right, so I'm going to put, and the first assignment will be due this Tuesday. Okay. So I'm going to put right here on announcements, see this announcement. So as much of our homework for the rest of the semester will be through an online system called web work. Startup instructions coming here soon. Okay, so when it gets posted, this will be updated to give you just how to get there, how to get started, and then we'll just dive right in with the first assignment due Tuesday. Okay, so like certainly by like noon tomorrow, maybe by the end of the day today. Okay, we'll get this going. All right. Any other questions or announcements? Please come in and look at your exam. Okay, so lots of you missed lots of questions, and we need to understand it. It's, everything builds on what we've done before. So come in and look over your exams and shore up your understanding and things that you missed. Okay? One person came in yesterday to look at their exam, and they got a high A. All right? So that's great, but if you struggled on the exam, you need to be in looking over your exam. Okay? So come during office hours or make an appointment with me to come see it. All right. Other announcements, questions, things I'm forgetting? Please. Yeah. Yeah. Okay. So last semester, as the mastery exam approached, lots and lots of students asked me this similar question. What is it? Oh no, I'm freaking out. Okay? I've got you covered. Just stay with me. You'll have, by the time the mastery exam comes, you will, if you have done your part of the deal, I will have done my part, and you'll be ready. Okay? So there's no reason, and it's kind of an unfortunate name because it doesn't mean mastery of the whole course. It means mastery of a very specific thing that we're kind of going to start today. So it's only like a sliver of the whole course that you're mastering. So don't feel like this is a comprehensive exam of everything in the course. It's the opposite of that. It's a very specific topic in the course, and we will get you there when it's time to take the test. If I haven't gotten you there by the time to take the test, we'll delay the test. Okay? So just take a deep breath. There's lots of anxiety last semester. I will get you there by the time we end up having the exam. If you do your part, you'll be ready. Yes, sir.
When is it? April?
What's it? I don't remember. A week or two? 2 weeks? April 1st? April 1st is the first attempt at it. Okay? And like I said, if that needs to be pushed back, we'll push it back. Okay? We'll push it back. Is that clear? So you can you don't have to be anxious. You don't have to ask me about it because just stay with me. Stay on top of the items in the course. But when the mastery comes, you'll be ready. Okay, so you had a ball that was thrown up in the air on your quiz. And so let's one last time, let's talk about, this is approach number 1. And so what on the quiz, the very first question. Our goal in the course right now is to start with a what? Exact accumulation function. And our goal to take that exact accumulation and determine a exact rate of change. That's our goal in the course right now. So we have 2 approaches to that. This is approach number 1 that we've been working on for since before break. So I want you to have a conversation with the person next to you. Make sense of what you're seeing in light of that goal. We're starting with exact accumulation. We want exact rate of change. One last conversation. What are you seeing? Go. There's lots to talk about up there. No, I said it's not a step. This is approach number 1. The quiz is approach number 2. This is not like your quiz. That's the point. This is not like your quiz. All right, let's see how we're doing here. Where's Travis Dillon? Travis. So this is a lot. There's lots going on here. Where does it all begin, Travis? What are we looking at first? In all this stuff, where does it begin? Approximate what? It starts with an approximate accumulation function. Agree with that. Nathaniel Gayton. Yeah, do you agree with that? It starts with an approximate accumulation function. Exact accumulation. Where do we see the exact accumulation up here? Right, okay. This is where it begins. We have an exact accumulation function. In this case, the height of the ball with respect to time since the ball was thrown. Okay? And so, take it one more step further. Nathaniel. Yeah, what happens next? Approximate accumulation, which is built based on what? Based on what? Or what does that function look like? How do we build that? Yeah.
It's based on h, so you're using h as an interval of points.
Okay. And then what will the graph turn out to be like? Piecewise. Piecewise linear, right? So we're going to use intervals of h and make this approximate accumulation function. This is approach 1, right? This is approach 1, which is different than your quiz, right? Different than your quiz. All right, where do we go from there? Where is Krista Marble? Where's Krista? Yeah. Where do we go from here? And what's that like? Tell me what that's like. Right, so we pick off for each one of these linear pieces, we get a constant rate, which forms a... Oh, it's supposed to. Where'd it go? Well, there it is. Yeah, so it forms a step function for each of those constant rates. And so that step function is just the rate for each piece of the accumulation function. So we just take the rate, that's our k right there. K, x minus a plus b. So the k part then is our constant rate function. All right, what do we do next? Where is Alejandra Casas? Yeah.
So then we make h small.
Yeah, exactly. Good. She said we make h small, and what does that do for us?
It makes the rate of change more exact.
Yeah. So it makes everything better, right? It makes the approximate accumulation better, and it makes the approximate rate of change better. Until things get really small.
Until they're virtually the same thing?
Yeah, so look at our approximate accumulation function. Virtually the same thing, and when we get really small, we can't even really see the steps anymore, but those are steps. But this is giving us a very, very good idea of what the exact rate function is.
I can see the steps already.
You can still see them, but not if you're in the back of the room. And so when h gets really, really small, then we have this, right? So we have the exact accumulation is virtually the same as our approximate, and then we get the rate function. Okay, so that was approach 1, and this is it. We're done with that. What did we say? This is great because this approach is great because it makes sense to us because of the month we spent on the forward process, right? We went from exact rate to these steps to a piecewise linear to the exact accumulation function. So this, we could hold on to this, and this is good. But in our goal to make an exact rate function, this is inconvenience. Okay? This does not lend itself nicely. It's a little complicated, and it doesn't lend itself nicely to getting the red graph, right? The exact rate function. So then we said, we're going to start over. And we're going to do approach 2. We're going to do approach 2. And what was approach 2 like? Okay, this is approach 1, right? Approach 1. And we said, oh, I got to get this back to 3. And look down at the bottom on the x-axis there. Is that reflecting approach 1 or approach 2? What I'm showing on is that reflecting 1? It's reflecting approach 1, where you have these fixed intervals of width h. Okay? And now we said, what if it was like this, like the blue one? That's 2. And so we said, let's look at it this way instead. So we have x, for every x value, you're going to get a different rate of change, but still with an interval width of h, starting at that x value. Rather than this chunky constant rate thing, we're going to get, for every x value, we'll get a continually changing rate of change. Okay? So on your quiz, I said, look at x equals 0.1. See how long this takes me. Start the clock. Oh, there. Okay, there we go. All right. So here was I said. Let x be 0.1. So let's pause x at 0.1, and let's find the constant rate of change that would realize the same change as the ball actually did. So you get your height at 0.1, and we'll call that like 1.45. So this point right here gives you that you started at 1.45 height at 0.1 seconds. And then 0.3 seconds later, the actual height is what? About 2.2. So those are actual values. At 0.1 second, the height was 1.45. At 0.4 seconds, the height was 2.2. So now in between, we're going to assume, instead of assuming this changing rate, we're going to assume the constant rate. The constant rate, and we're going to take that constant rate from that blue line right there and assign it to, so we get this constant rate from its slope, and then we're going to assign that constant rate only to that one point, not to the whole interval. We're going to assign that constant rate just to x equals 0.1. So how do we represent that on the left graph? What kind of thing will represent this constant rate at that moment in time, 0.1?
You find a constant rate by doing the math, and then you put it on the marker at 0.1.
Okay, and so what will represent it over here?
A single dot at 0.1 is about 2 2/3.
Yeah, so when I did it, I don't remember what I got, but I got 2.5 is what I got, I remember. So if you do this, you get 2.2 minus, so k is change in y over change in x. So our change in y is 2.2 minus 1.45 divided by 0.3, and I get 2.5 for that, for mine. So you could have something slightly, as long as you're like between 2.2 and 2.8, you're in the ballpark. Okay, so then at 0.1, we're going to assign that rate of change only at 0.1 seconds, because as soon as x increases a little bit, we're going to have a different rate. We're going to have a different rate. So it's not steps anymore. So this is the point, 0.1 seconds, 2.5. What are the units on the 2.5? 2.5 what? What does that number mean, 2.5?
Meters is height. So
It's a rate of change. So it's going to be, is it meters or feet?
I honestly can't remember.
Meters.
Meters per second. So at 0.1 seconds, and is that an exact rate of change or approximate? it's based on this blue constant rate, right? Over that interval, which is, so is it going to be less or greater than the actual? Do you see that the rate of change will be less? The rate of change will be less by comparing what the relative size of changes here is to what we calculated by the blue line. Okay? So there it is. So up to that, so that's that 1 point. Okay? And then you did that 2 more times. You did it for 0.45. And when you do it for 0.45, see how long it takes me? Do better. Oh, I had it. There we go. So for 0.45, you draw this picture. And you calculate that constant rate, and we're going to take that constant rate and assign it to the x value at the beginning of the interval. And we're going to get this point, 0.45 and like -1. Hopefully you're feeling good about your quiz right now. Are we?
No.
Yep. Yeah.
Some yes, some no. Okay. But if no, so let's get it. So rearrange your thinking and get in line with this. Okay? And then we did it for 0.8. So we're going to move x out to 0.8. And then I think that's like something like -4.3. That's what I got. So at 0.8 seconds, -4.3 meters per second. And so then I said, if we did this for every point, if you did this for every x value, all the way up to, what, 0.9, what would it be? It would be a bunch of these points, but now not a step function, but a continuous locus of points like this. In this case, it turns out to be a line. Okay? So our rate of change function is a line. Is that line an exact rate of change function or approximate? Approximate. It's based on all these constant rates for h of 0.3. Okay, and so yeah, that was the last question. Last question was, what did you make? You made an approximate rate of change function, which in this case, for this particular projectile, turns out to be a line. Okay, questions on, so this is approach 2, and this is what we're abandoning approach 1, and everything is going to be about approach 2. So if we want to write this, this is R2 of x. We want to write a general formula for that. Okay, well, we can just come here and just call this anything. So now this is any x value. So this is any x, so just ignore where we're at. So this, where I'm placing it, I could have placed it anywhere. So how are we going to, what is that R2 function going to be? What's the structure of it? So what's the overall structure of the R2 function? Adam? Good, right. So because it's the rate of change at a particular x, the overall structure is going to be delta y over delta x. And what do we need to calculate delta y over delta x in this situation? How are we going to get delta y? Yeah, change in y. So we need the coordinates of these points. So delta y is going to come from this y coordinate, final y, minus initial. So we need to write down the coordinates. And this is actually easier. Approach 2 is easier. This is easier, right? So what are the coordinates of the first point? We're going to call our accumulation function f.
2.5.
No, this is any x value. It's any x value. We're writing a formula now. So it's x and f of x. And then what's the x coordinate at the end of the interval? And you guys are becoming mathematicians. Okay? And so what's the change in y? Over? Yeah, you could do that minus that, but what is delta x? H. There it is. This should make perfect sense. It's a rate of change. It's delta y over delta x. It's the final y minus the initial y over the change in x. And this is, again, approximate or exact?
That's approximate.
Approximate. How could we qualify that and say, oh, it's exact? It's exact if what?
H is very, very, very small.
H is very, very, very small. Right, so when h is very, very, very small, it is exact. Approach 2. This is where we live now. So we're abandoning approach 1. Approach 1 was great because it related so well to what we did before, but this is how we go forward, because that's a lot easier than the one that has left in it, right? The one that has left in it, not convenient. This, a lot more convenient. And it works just as well. So we've got there's the exact one that we found from approach 1, and if we make h smaller, so if I make h smaller, each time I make h smaller,
Get closer.
it converges on the actual rate function until they're indistinguishable. So in this case, for h equals 0.005, in this view of it, the human eye can't tell the difference. So this is for h equals 0.005. Okay, so we have this thing of, we've seen this idea a couple times now. Close enough that we can't tell the difference. Super, super, super small. Okay, so we want to formalize that now. This is what limits are about. Okay? We've seen this twice, so now we want to formalize this. Okay, so here's a picture that kind of encapsulates the idea of limit, in that a limit is a never-ending sequence. Right? So we think about h getting smaller and smaller and smaller and smaller, and we have to keep doing that over and over and over again until like we said, you can't tell the difference. So this is, as the light bounces, it's like it keeps going on forever and ever, never-ending sequence. Okay. So that is similar to the idea of limit. Okay? Limits in mathematics. Two representations of the same number. Okay, so agree or disagree? If the symbols a and b, or variables a and b, represent different real numbers, then it's always possible to find a number between them. For instance, their average, a plus b over 2. Agree or disagree? Okay, so if you have different numbers, no matter how close they are together, you can always find a number between them. Cool. All right. How about this? If the variables represent a real number and it is impossible to find a number between them, then they have to be the same number. Is it okay? All right, it's going to get really uncomfortable in a second here. Are you sure you agree with these? Are you sure you agree with both of these? If they're different, you can always get a number between. If you can't find a number between, they got to be the same. Okay, so what about this? 0.999. And so the ellipses, dot, 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 means keep adding nines forever. Keep adding nines forever. 99999. They never stop. Okay? So find a number between that number and 1. Can you find a number between 0.999, when the nines go on forever, and 1? Can you find a number between those two numbers? So therefore, by conclusion number 2,
Exactly, agree and disagree.
they're equal. If you keep adding nines, 9, forever and never stop, it is equal to 1. He's on board.
You tell me that, I believe you.
Is it cool? Is it uncomfortable? So, if you think they're two different numbers, then my challenge to you is, tell me the number that's between them. Find me the number that's between the 0.999 going on forever and 1, and then then you could say that they're different. So what is the number that's between them?
0.0000000 infinite 0 and then.
No, you're way off there.
No, I totally agree.
Okay.
In between,
In between the two. 0 is way less than 0.9, right? 0.000.
not what adds up
Yeah.
to it.
Okay. Anyone want to protest? No. Okay.
I don't
All right.
know.
So, but kind of our idea of limit was if you had, for one person, if you had 1,000 nines, it said, this is close enough to 1. I'm cool. They're the same. For someone else, it'd be like, nope, you could get a number between them. So I want 1,000,000 nines. And that's close enough for me. Now they're virtually the same number. Someone else, that's not enough. So he takes 1,000,000,000 nines, okay? 0.999, 1,000,000,000 nines. He says, that's close enough for me. So that's the idea that when you get so many nines, it's like they're all the same. It's all the same number because they're so close that it's indistinguishable, okay? So here's the formal mathematics behind this. 0.9 is 9/10. 0.09 is 9/100ths, and then we have 9/1000ths, 9/10,000ths, 900,000ths, 9 millionths, etc. Okay, and so then this notation right here means we're going to add up this sequence of values where that n just gets larger and larger and larger. And when you do that, it's equal to 1 because you can't find a number between. So this is our formal limit notation. Please.
What is that symbol graphic with the infinity? You may have marked it down.
Infinity?
No, it was just part of the.
Yes, part of it. Okay. All right, so this right here then is our, where is it? This is our formal notation then that means take this never-ending sequence. Let n get infinitely large. Okay, let n be 1,000,000. Let n be 1,000,000,000. Let n be a Google. What's a Google? You know what a Google
One
is?
followed by 100 zeros.
What's that?
One followed by 100
Right.
zeros.
Right. It's 10 to the 100th. That's what a Google really is. Okay, that was long before it was a search engine. Okay. Okay, so that's what this means. Just let n keep getting bigger and larger and never stop. N goes to infinity. So we've seen this idea of limit twice. Okay. We've already encountered this twice. So let's look at that. Okay. Recall our approximate accumulation function when we were on the forward journey. Okay. What did we say? We said that when delta x becomes sufficiently small, we'll call delta x equal to dx. And then when delta x is dx, what did this thing equal? Should all know this. What did our accumulation function become when we let delta x be dx? Our integral function, right? Our integral function. Okay, so now we have a different way to formally write that. So alternatively, now we can go back to the original form, and add the limit as delta x goes to 0. So this never-ending sequence of letting delta x get smaller and smaller and smaller and closer to 0 is in effect the same as what we did with dx. Okay, and so that equals the integral function as well. So here's a different way using this is our formal limit notation that would get us this last step of the process from approximate accumulation to exact accumulation. Okay, and now we've just seen it with the rate of change function, right? So now we can put that the limit as h gets very, very small. Okay, so approximate accumulation, let delta x get very small. The limit as delta x approaches 0, you get exact accumulation. Okay? Approximate rate of change, that's just the ratio delta y to delta x for any size h, but let h get very, very small, exact rate of change. So this is a formal mathematical way to talk about the last step in both of the journeys, right? From approximate accumulation to exact accumulation. It's the limit as delta x approaches 0. And then from approximate rate of change to exact rate of change, this is the limit as h approaches 0. And h is just our new way to write delta x. They're virtually the same, just a little shorter, a little cleaner. Question, please.
So the limit as delta x goes to 0. Okay, so as a whole, it's an exact
Right.
accumulation, but it's equal to the integral from a to x.
That's our exact accumulation function, right?
Just use that because it's easier.
Yeah.
I mean, both ways, it's right.
Yeah, they're both sides of those are exact accumulation. Yeah. So I'm just giving you an example of how we could apply now this limit notation to what we did before. But yeah, so when we want exact accumulation, we're going to write it as integral. That's right. But, okay, so this is a good point. So when we write exact accumulation, we're going to write integral. But when we, and is that open form or closed form? Open or closed? Open. Okay, so when we write exact rate of change, we're going to write out this. And is that then open or closed form? Does it reflect a process? Or does it spit out results rapid fire? It reflects the process of finding the approximate rate of change and then letting the interval get very, very, very small. So this is open form of a rate of change function. This is open form of accumulation function.
I might be jumping the gun on this one, but that h to approaching 0, is that from the positive or negative side? Or is that,
So the way that we had our drawing, h was a positive value, so it'd be getting smaller and smaller positive values. Yeah. Okay. So limits. Let f be the area of a square with side length x, that is f of x equals x squared. What's f's rate of change function? So now we want to go through this approach number 2 process, but symbolically. So what was r, so this was r2, right? r2 of x is the rate of change function. And what is that? We should know that. This is where we're living now, right? It's delta y over delta x. Change in y over change in x. Okay, so if we want the rate of change function for this particular function f, we're going to apply this rule to the function f. So what does the rule tell us to do with the input in this function?
Square.
Easy. It just says take the input and square it, and that's the output. So now we're going to look at this right here.
But isn't that a closed form?
What's that?
Isn't that a closed form?
Sure. Yeah, it's a closed exact form of accumulation, right? Accumulation of area. So we'll start with that part right there. So what's the input in that expression that I've circled in red? What's the input? X plus h. Think of that as a unit. X plus h is the input. And what does the function tell us to do? Square the input. So that's going to equal? So you just told me x plus h was the input, and this function says take the input and square it. That's what's in the red, what I've circled in red is that. Okay? F of x. Hopefully that's really easy. So this is our rate of change function, okay? Is this approximate or exact? Depends on the size of h, right? But we don't want h to be there. So as this h is here, we'll just assume for now that h is not small, okay? Not small, so that's an approximate rate of change. So we want to, if we make h small, our problem is that what happens? It's like virtually 0 in the denominator, and that things go haywire, right? You can't, unless you're oh, what's his name? I can't. The joke is ruined. I can't remember his name. Pathways guys, what was the joke? Remember? Who can divide by 0? What's his name?
Oh, Chuck Norris.
Chuck Norris can divide by 0, but you guys can't. Okay? So, all right.
It's undefined if you divide by 0.
Right, but Chuck Norris can do anything.
Yeah,
Can you count how many tons of concrete there are in the country?
Okay, here we go. So we're going to, the problem with this form of it is that we can't, like algebraically, we can't evaluate this limit because it would be like this getting so small in the denominator that it's virtually zero, indistinguishable from zero. So that's problematic. So we need to do some work on this to eliminate this h out of the denominator. So we're going to work on that part right there, which is going to be from your 8th grade days. There's 3 terms in that binomial square, right? And what happens now do you see that we've got something that simplifies in the numerator? Positive x squared minus x squared goes away. So we got 2xh plus h squared over h. Why is this helpful? Because now every term has an h, and we can factor out h. And now this fraction that used to have an h in the denominator, that was problematic, after we factor out h, that's when we can eliminate h from the top and bottom. And we get this. So our approximate for x squared, our approximate accumulation, approximate rate of change function becomes the simple version 2x plus h. When we do the math right? When we do the algebra right, we get this very simplified version of approximate rate of change. And what's the link between, what's the idea from approximate rate of change to exact rate of change?
Very small.
Right, and that's, so we could apply our limit, right? So we say exact rate would be limit of that thing. And that's symbolically how we think about let h get so small that it's indistinguishable from 0. And so then when h is indistinguishable from 0, then this whole thing is indistinguishable from 2x. And so we got it. Exact rate of change. See how much nicer that is without the left x hanging around, right? So this, with left x in the picture, it's ugly, okay? The left x is nice for a visual process, but when we start doing it by algebra, we want approach number 2, right? Without left.
Give us another.
What's that?
Give us another.
Oh, we'll have more. You'll have more. Okay, so any questions? Okay, so this is where we started. X plus h squared minus x squared over h. And so now here's a new symbol. This is another symbol that kind of encapsulates the limit idea. That these values of these two expressions are essentially equal for exceedingly small values of h. Okay? Another angle on this, another way to formalize this idea of limit. Okay, so that equals with a dot means they're essentially equal when h is very, very, very small. Okay? It means that both expressions produce the same number for sufficiently small values of h. All right, so let's just do an example. So let's let our side length of our square be 5. Okay, so our side length is 5. And let's let h be 0.001. That's not really small, but that's small. Okay, that's kind of small. Kind of small, okay? So I want you to find the value of both sides of the expression. So on the left, what does it equal? And on the right, what does it equal? So do that fast. So what are we doing? So on the left side, we're saying 5 plus 0.0001, that all squared, minus 5 squared, over 0.001. As soon as you get it, shout it out. 10.001. That's the left side for this smallish h, kind of small h. And what's the right side when x is 5? 10. Okay? Versus 10. Okay? If we made h 0.00001, then I'm guessing it would be 10.00001 on the left and 10. So you see that as h gets smaller and smaller, it gets closer and closer to 10. And when h is very small, we just say they're the same number for all practical purposes because they're indistinguishable. They're so close. And if it's not close enough for you, make h even smaller. That's the idea of the limit. Okay? Okay? If we let h approach 0, there's no number between them. We talked about that. There's no number between these two. Okay? And then we can say the limit as h approaches 0 of that quotient there, the rate of change quotient, equals 2x. Questions on limit notation? Does it make sense? So all these 4 things mean the same thing. Okay, so let's talk about something different from limit for a second. Let's talk about accumulation to rate to accumulation. Okay, we just learned that if f of x equals x squared, the rate of change of f is 2x. We learned that, right? So thus f can be expressed a different way. If the rate of change of f is 2x, then what's another way we could express the function f? Talk to the person next to you. What's another? We got another way. Now that we know the rate of change function 2x, there's another way to express f. Go. What is it?
You need to write it down.
How can we express f if we have its rate of change function? That's what we're saying. Has anyone learned something in the course? How can we express f if we have its rate of change function? Okay, where's Lydia? Sakala. Where's Lydia? Right there. What did you say? Well, so how else can we express f?
We thought of it as 2x squared minus 1, as in 2x, 2 times x to the power 2 minus 1.
2 times x to the power. Oh, that's just a rule you learned before. We didn't do that. So how can we express it in a way that we have learned? But so yes. Yeah. So that's right, but that's you learned a little trick from before, right? So, in this course, what have we learned a different way to express f if we have the rate of change? I know that Dima knows. How about Brenda Nieto? Where's Brenda? Okay, remember, you get an attendance hit if you don't respond. Patrick. Where's Patrick? How else can we express f if we know its rate of change is 2x? Okay, what integral? Good. What integral? Zero to x of t squared or of 2t? What's going to go inside the integral? T squared or 2t? 2t. Okay. If you didn't come up with that, you should have, okay? This was the whole last month and a half we talked about and built up to this, that we can write, given a rate of change, an exact rate of change, we can write the accumulation function this way. Is it at least familiar? Okay. So this is really important. But this means that we just learned something else. Okay? So we didn't just learn that 2x is the rate of change of x squared. We learned something else. What did we learn? That the open form of the integral a to x 2t dt. So back when we were doing integrals, we said, what? We said we don't have a closed form. We can only express these exact accumulation functions in open form. But now we have a closed form for that open form integral. What is it?
Square root of x 2t.
Sorry, did I say that wrong? We have, so if we were starting with this open form integral, before we said we don't know what the closed form is, but now we know what the closed form of capital F is. What is it? It's x squared for some value of a. In this case, a0. So when you get a closed form rate of change function from an accumulation function, you don't learn just one thing, you learn two things. You learned what the rate of change was, but then you just established for yourself a closed form for an open form function, open form accumulation function. Does that make sense? Yeah.
What is the value of a? I don't see.
In this, well, so our general version of the open form is a to x. So in this case, a is 0. In this particular case, a is 0.
Zero, sorry.
So every time we get a closed form rate of change function, we learn two things. We learn the obvious, and then we also learn a closed form for an open form accumulation function, or open form integral. Okay, so now you try. Last class we learned that the rate of change function for a volume of a sphere was 4 pi x squared. So given this accumulation of volume of a sphere, we learned that the rate of change was 4 pi x squared. So what else did we learn as a result? Okay, what else did we learn as a result? Talk to the person next to you. Work it out. Go. Okay, where's Rachel 2? Rachel 2. All right, Rachel, how'd it go? What else did we, so if we know that the rate of change of volume is 4 pi x squared, what else did we learn? So we determined that the rate of change of this function was a closed form of 4 pi x squared, and that means we learned something else. What else did we learn? Exact accumulation. Of what open form accumulation function? So if we had nope, not x squared, not x cubed. Was it? Go ahead. Yes, you're going to do it. Go. Integral? Yep.
4 pi
Can't use x.
or t.
T squared. If we had that open form integral, what did we learn? Now we have a closed form for that. What is it? What is it? No, closed form, like a rule, a closed form rule. What would it be?
Yeah, it would be a v of x equals 4/3 pi x cubed for some value of a.
That's right.
And this is the,
So
like,
here,
most-
before we said, if you had an open form integral, we have to use technology to evaluate that. We don't know what that is. But now, for this particular open form integral, now we know we have a closed form, 4/3 pi x cubed. Right? Because this is the accumulation of volume, and this is the accumulation of volume. So I should have... Okay, so does it make sense what I'm getting at here? So we'll keep practicing that in the coming weeks. All right, so let me talk about some notation. So let f be any function, okay? We're going to use this notation to denote f's rate of change function, the function whose values, whose output, give the rate of change of f with respect to x. Okay, that is, this is our, which we know is our rate of change function for f. That's our rate of change function. Okay, is it, so this notation, r f of x, does it give approximate rate of change or exact rate of change? Does it give approximate rate of change or exact rate of change? Depends on the h value. So the thing about this notation is we're going to let this notation be flexible, okay? It's going to be flexible. For a non-small h, it's approximate. For a really small h, it's exact. So without including the limit in there, without including the limit notation, this notation, the rate of change of f through r sub f of x is gonna be flexible for us, and that's just helpful. Okay, we know that if h is not small, it's approximate. If h is really, really small, like you're evaluating the limit as h approaches 0, then it's exact. Is that okay? So this notation will be kind of our go-to notation. We can use it anytime. We can use it anytime. So reading the notation, it's the rate of change of the function f with respect to the input x. The rate of change, and you just read it left to right. Just read it to left to right. It's the rate of change of the function f with respect to its input x. Okay, we're going to do this, but we're out of time.